So James is going to talk to you about the new module within Adaptiiv. Yeah, over to you, James.
Thank you, Misbah. Let me just share my presentation. And thank you everybody for attending this afternoon. I'm really excited to tell you about this. You may actually know Adaptiiv Medical because we're the ones who brought 3D printing really into radiation oncology, at least in the commercial space. But today I'm going to talk about something that potentially has no connection with 3D printing at all. It can have, but it can be completely independent, and that is planning automation. And here we're thinking about skin, particularly. Of course, you've seen various forms of planning automation. This is a site-specific tool that I'm going to be discussing. And so today I'll introduce the tool DermaPlan RT. It's quite new. In fact, we will just be launching it at Astro, which begins in San Francisco this coming weekend. I'll explain, since I imagine some of you are physicists here, I'll explain how it works, since you like to see under the hood a little bit, or the bonnet, a live demo in Eclipse, and then this is photon planning. So I really wanted to address, a comparison between megavoltage photon planning versus electrons for skin. So I hope that's a good plan for you today. A little bit of a story. We at Adaptiiv partner very closely with Varian. In fact, we were the first member of their 3Co system, which is like a organization for other third-party products for compatibility and sales and so on. And Varian disclosed that their halcyon users or potential halcyon users were kind of struggling with skin sometimes at the planning step because they were used to having electron beams. And somebody there said, wouldn't it be great if we had an automated planning tool for halcyon? So that was the impetus for the initial development of this, although we realized that this could be really useful for every platform providing megavoltage photons, so also true beam, edge, ClinAc, and so on. So where would you use DermaPlan RT? Anywhere where you might use electrons. So these are going to be superficial targets. Extending to the surface could be just a few millimeters thick or up to about 3 centimeters deep. Could be anywhere in the body, scalp, face, chest wall, extremities, and so on. Could also be a lot more complicated than what you see on the screen here. DermaPlan can tackle cases like whole scalp, where you have 360 degrees of treatment on the scalp, or indications, volumes wrapping around extremities. I'm not going to get into the tool just yet, since probably doing a live demo is the best way to show it, but suffice it to say for now that this is run from directly within Eclipse. The input requirements are pretty minimal. You just need a CT with a body contour and one target volume. You can incorporate organs at risk as well. And our goal in developing this was full automation, so generation of a plan, a dose distribution with a single button press and no user interaction. And we've met that goal. So how does this actually work when you hit that generate plan button on the bottom right? Four steps, and this is a form of AI called ARIR, so automated rule implementation and reasoning, and this has been used in various forms of automation. So it's not a convolutional neural network or anything like that. It's reasoning, and it's kind of behaving like a dosimetrist would. So step one behind the scenes is if you have a PTV, the system will examine that PTV and generate a bolus based on that. I do want to mention that bolus can be kind of irregular in shape, that is mirroring the shape of the PTV at the surface plus a margin. That is going to give you, not a shape that's rectangular likely. And so that would be quite amenable to 3D printing if you wanted to. The second option for that bolus is a superflab style bolus, so a vinyl sheet style geometry. Step 2, or step 1B here, is extending the PTV into the bolus a little bit as a planning construct. That's done to avoid creating an interface, which can be problematic for optimization right at the surface. Some strategic tuning structures will be added as well to enforce dose conformity and compactness. Step 2 is probably the most interesting step. This is beam placement. So essentially the system and the tool examines again the PTV geometry and sets up a set of beams for IMRT or 3D conformal modes. And there are a couple options for geometry determination, which I'll tell you about in a moment, or sets up start and stop angles for arcs. So if we think about beam placement, what a planner would probably do, given a PTV like this, is a kind of tangential approach, right? And so that's the first option here. The tangent line will be determined automatically, and then a set of beams will be based on the tangent. One pair, really glancing the tangent likely, and the rest at a specified minimal angular offset from that. So that's option 1, and that would apply to IMRT or conformal planning. Option 2 is pretty smart. It examines at quite a fine granularity all candidate gantry angles. And for each gantry angle candidate, calculates the volume of normal tissue that would be exposed by that beam, given the PTV geometry. And it does this very fast. And at the end of that, it will pick N beams, where N is supplied by you, the planner, with the lowest volume of normal tissue exposed, again respecting a minimum angular separation of beams. And comparing those two techniques, we've looked at multiple sites, multiple target volume geometries, and you can really see the effect between a tangential approach and with this peripheral dose optimization. So here I've turned on a fairly low isodose for this cheek indication to show the effect. So if you look at this arrow over here on the left, yellow arrow, the same location on the right, you can really see a compactness sort of at the low to intermediate dose level by employing that technique. Step 3 is optimization. If you're doing IMRT or VMAT, the system will leverage your default optimization algorithm defined in Eclipse. So this could be, for example, PO 16.1 or 18.1. And then finally, a forward dose calculation. If it's IMRT, of course, leaf sequencing before that, and then a forward dose calculation. And again, your default volume dose calculation will be determined and accessed. So there's really no commissioning involved here, just because all of this leverages what you've already commissioned in the system. That is your optimization algorithm and your forward dose calculation. So the result of this is a plan, a brand new plan, and we're going to try this in a second. And this can be produced within just a few minutes. Typically, at least on my system, this is a couple of minutes for IMRT and probably about 5 minutes or so, within 5 minutes for VMAT with a couple of partial arcs. So with that, let me stop sharing that and let's jump over to an Eclipse box. I hope you can all see this okay. I have loaded this very unfortunate test patient who's got lesions all over the scalp and the face. Great case for testing. So you can see that we have a couple on the scalp. We have one on the nose, cheek, and left ear. And we can pick one of these and do a plan. The nose is one of the more complex ones that I have in the set, just because of its interesting shape here at the surface. And so all we're going to do to start this is to go to the Tools menu, Scripts, and then I'll start DermaPlan here. you can set this up as a global script so everybody in your facility could access. So here's DermaPlan. I'll give you a bit of a tour of the other tabs here, but we're going to go straight to where all the action happens. And all we have to do here is to specify the structure set we want to use. So and it will put the most recently created structure sets first here, so they're easy to find. Let's pick our PTV nose. And in beta testing of this, one piece of feedback we got from users was there's usually one priority organ at risk for skin cases proximal to the PTV that you might want to protect, sometimes not. But in this case, it would be the left eye. So we'll protect that. We'll enter a dose. This will work regardless of whether you have configured Eclipse in gray or Senna gray. And let's start off with an IMRT plan. The defaults here are 8 beams with a minimum angular separation of 15 degrees. And you can see those 2 options here for beam placement. So I'll press generate plan. And you can see a little bit of activity going on down here. It's looking at the structure set and determining whether we have already run this on the structure set. If so, it will clean up any previous planning structures. And it's preparing those planning structures. Now you may see them appear in the background. There we go. So we have tuning structures, we have the extended PTV, we have the bolus already there. It's figured out that my default optimization algorithm is PO1610, and it's using that for optimization. And having completed that now, it is forward calculating a dose distribution, in this case using Accuros XB. Depending on whether this is IMRT or VMAT, the optimization step in particular will take different amounts of time between those 2 techniques. So it's quite a bit faster for IMRT, although I'm going to show you some results at the end of this presentation that will give a few votes towards VMAT as a technique for skin. So the plan here is we'll have a look at this completed plan. You can see that was about 1.5 minutes, 1 minute and 29 seconds here. A few reminders to kind of finalize the plan here, things that the planner might want to add to it, like tolerance tables and so on. We'll close that, and you can see the planning structures that I was describing: extended PTV, a bolus. We have a body that now contains the bolus, so it will be included in the volume dose calculation, although we preserve the user's original body. People would get angry with us if we disposed of that. And then tuning structures to use in the optimization. Here's our plan. Remember, we had asked for 8 beams, tangential approach. Here it is. And if we zoom in a little bit on this, I'm just going to turn off the fields to clear this up a little bit. I like to look at dose wash. So you may have noticed on the UI of DermaPlan RT that we had normalized covering by the 95% isodose surface. So we'll look at coverage first of all here, scrolling through. You can see my maximum dose is 103 or so in this distribution. And you can see how the dose distribution extends into the bolus. This is intentional, of course, to try to create a uniform dose right at the surface where we want to, rather than creating a boundary there. For dose compactness, if you were using a metric like gradient index, you might be interested in the 50% or so. So we can have a look at that too. So there's an IMRT plan. I think a good idea for us now is we'll go back into DermaPlan. I'll give you a bit more of a tour of it, and then we'll launch a VMAT plan. And while that's calculating for a few minutes, I'll tell you a few more things about this application. So you've seen the planning tab. You may be wondering, what were the optimization parameters used in automated planning? We worked very hard at finding a simple but effective class solution for optimization. So that's in the background here, including normal tissue optimization. You can access these if you want to and change them, but we're finding that for like 90% of the cases, that's not necessary. You might also wonder, how do you set this up to use your particular treatment unit in Eclipse? Very simple. You specify your treatment units, here the energy that you want to use. So if it were a halcyon unit, it could be FFF. You would enter a dose rate, and if applicable, whether or not you want jaw tracking, you can save that as a profile, and you can select it here. So let me, since I'm going to do another demonstration, I will go back to TrueBeam, 6x 600 MU per minute with jaw tracking on. And then options, we have a few options, whether Eclipse is in centigrade or gray. And in addition to deciding on whether you want a sheet bolus or an irregular bolus, well, what's the thickness of that bolus? What is the margin of the surround around the PTV? And then if you want to change its Hounsfield unit in the calculation, you can. For example, if you are using a 3D printed bolus out of TPU or something like that, you could specify it here. Tangent offset is an offset of the default, that is most posterior tangent beams that we saw in that plan. You could tip them up or tip them down if you preferred. And then for conformal mode, what is the margin of the MLC around the PTV projection, and whether or not you want to weight a trimmer beam in that. So let's go back to create another plan. I'll use the Xeil 02 set here just for comparison. Let's do the nose again, protect the left eye. The dose here is kind of inconsequential to us, but let's do a 2 arc VMAT plan with partial arcs, and we will set that into motion. So that'll take a few minutes, and so instead of just leaving you with total silence, I'll stop sharing that, and we'll jump back to presentation here. So you can see the automation of this, and you've seen just one case so far. What are we seeing when we create these plans in terms of plan quality? And the most common question that we get is, since electrons have been kind of the mainstay for megavoltage treatment over the past decades, how does the dosimetry compare? And so on the top row, we have, in this case, I've covered by the 90% dose in all cases, and you can see the 50% down the bottom row. We have columns of IMRT, automated, VMAT, automated, and electron manual. Really a couple take-home messages here, and you can probably see it already. The first is much better dose conformity at the PTV normal tissue boundary here, the distal aspect of the PTV. Compared to electron planning here, where unless you're using a kind of advanced tool like a modulated electron bolus, you really have little control over that with electron planning, and you're picking an energy, of course, out of a coarse set of energies to cover just the deepest aspect of this target volume. The second point, you can see it here in the top row. This hotspot here, which I guess in this example is about 123%, you really have little control over that magnitude as well as where it lands. And of course, through optimization of photon techniques, you have a lot of control over those parameters. So there's a nose example. Here's another common site, of course, the ear, left ear in this case. And similar behavior. You can see the conformity at the deep aspect, dose uniformity at the surface, compared to electron planning, where yes, we cover, but we also treat normal tissue inadvertently, and we have to kind of live with this hotspot that occurs. And then here's an extremity, same columns, same rows. Arguably not a bad electron plan here, although really high hotspots. The planner actually could go back and work on that potentially. Pretty good conformity of the electrons at the deep aspect, although that's really just due to the simplicity of the geometry at the surface here on this leg. Okay. I'm just peeking back at Eclipse here, seeing how it's doing with our VMAT plans. It's on the forward Acuros dose calculation right now. So let me show you something that's hot off the press. This is a collaboration with Dana-Farber Cancer Institute in Boston and Harvard University. This was a 20-patient study. Dana-Farber was one of the first groups to have DermaPlan RT. 20 patients sampled, so 4 cases each among scalp, nose, ear, and chest wall and extremity, using IMRT automated, VMAT automated, or manual electron therapy planning, and looking at comparatively conformity index, homogeneity index, and gradient index between those 3 techniques, as well as normal tissue receiving 90%, 50%, or 30% dose. And then, of course, we're also interested in a measure of total planning time. And so this is real world data. This is really planning time until this dosimetrist felt comfortable with the plan quality and deemed it acceptable. And so if we look at these basic dosimetry metrics, we have IMRT, VMAT, and electron conformity index. This is the PITV definition of conformity index, not Paddock, so lower is better. And you can see that both IMRT and VMAT substantially lower than electron plans here, and statistical significance here between both photon plans and electrons, as well as much lower variability in the conformity index. So really tight control with the photon planning. Homogeneity index, so that is what is the significant hotspot in the PTV divided by the coverage isodose level. Similar behavior, we've got significance between both photon techniques, much lower hotspots. So you can see it's around 107 here, median, compared to some of these electron plans where the hotspot might be, 20% or more greater than the coverage level, which you had seen in those distributions that I showed you. And finally, gradient index here. This is a look at the compactness of the 50% isodose surface. VMAT significant over and improved over electron planning, although IMRT actually quite comparable in that respect to electron planning at the 50% surface. Normal tissue volumes. So sometimes we associate techniques like multiple field IMRT or partial arc or full arc VMAT with a dose wash, right? But here we see at the 90% level, no significant difference actually between the electron plans. At the 50% dose, we have an improvement of VMAT over electron in terms of that 50%. Just slightly, though, although statistically significant. IMRT was worse than VMAT and not different than electron plans at the 50% dose level in terms of normal tissue volume. As we go lower, we see that both VMAT and IMRT not statistically different than electron plans. Planning time, big difference compared to, as you might imagine, compared to planning electrons manually. Here, IMRT was the quickest, really due to its fast optimization, as you just saw in the demo, also the lowest variability in planning time. And then VMAT was next, and then electron planning. The factor improvement of planning time was a factor of 5.6 for IMRT and 2.6 for VMAT. Okay, how are we doing back at our Eclipse workstation? Let's jump back over there. Our T-box. Yep, the plan complete. This plan, 2-arc VMAT, completed in about 3.5 minutes. We'll close this and drag in our new plan. You can see our 2 partial arcs here. Again, the tangent to the target volume was determined, and the partial arcs were based on that. You can see the same tuning structures here have been added to our structure set. Let's have a look again at the dose distribution, and I'll turn off the arcs just for clarity. So generally, as you might have seen in the past, if you've ever compared IMRT and VMAT, kind of a smoother, less streaky dose distribution. The hotspot was a little higher here, 105.3 than our IMRT plan, although still acceptable, I would say. And then, according to that Dana-Farber study, if this is representative, we should see a little more compactness at the 50% level. So there's a VMAT plan. Okay, I'll stop sharing that and go back just to wrap up our webinar here. So this is quite new, although it's been used in the US a little bit. As I mentioned, we're just officially launching this in about a week or less than a week. The physicists and dosimetrists who have used it, their first comment usually is about planning time and efficiency here. So here's a physicist at Rochester planning within 2 minutes instead of about 45 minutes. He would have done a lot of his cases with 6 MV VMAT, so was making that manual planning comparison. We have the author of that study, Josh Hempstead. This is when you see times like 3 minutes, 41 seconds. This is, as you could tell, the time that it took to generate the plan. The real world data is the box and whisker plot that I just showed you, factor of around 2 to 5 savings. This would be just for a single plan generation. And then some comments about just freeing up time to do other things for dosimetrists, as well as standardization. So affords treatment planners with varying experience levels the opportunity to hone their skills for complex skin cases. So it can be used as a teaching tool in a way. You can generate a plan, ask DermaPlan to do that. New dosimetrists or newer planners can look at what it did and use it as a bit of an educational tool as well. So just summarizing, DermaPlan, it's new. Automates IMRT, VMAT, and 3D conformal planning. I didn't show you a 3D conformal example, but the beam placement approach would be similar to IMRT. It would just be MLC-shaped fields and a trimmer field if you wanted one. We have planned a lot of cases with this and quite a variation in case geometry. Plan quality is uniformly high. You could see the comparison with electron planning. The metrics that really stand out are conformity and dose homogeneity improvements, although the dose wash doesn't seem to be significantly worsened, at least down to the 30% level or so. Plan generation within minutes and a lot of factor time savings, greater for IMRT than VMAT. And we're really hoping that for skin, whether you're on a Halcyon unit with no electron beams or you just want to speed things up, on a TrueBeam platform or something like that, that this should increase efficiency, uniformity, and plan quality. So with that, I will stop sharing and wonder if anyone has any questions.
Right, let's have a look in the chat.
Nilesh has a question.
Yeah, we've got some hands up, and I think there's one question in the chat. Should we start with that one? So
Yeah,
for
you bet.
evaluating this, do you offer either a trial license, or can sites send an anonymized patient to compare their own plans?
Yes to the first and no to the second. So yeah, I think a trial license can be arranged, and certainly we have done that with customers. It has a license that will time out after a period of time.
I think it's got a hand up. Sorry, I'm just trying to check who's Nilesh. Do you want to ask your question? You're muted at the moment. I don't know if you're.
Oh, we can't unmute. You can also type your question in the chat, and I think Stefano is typing a question right now.
Can you hear me now, or?
Yes.
Yes.
Oh, yeah, great.
Yeah.
So I was just wondering whether there was any like studies or any comparisons made with the organ stoses with manual planning compared to the automated planning, and whether there is a systematic difference in the organ stoses.
We haven't measured that particularly, although you can see with the difference in dose conformity compared to electrons that you should expect greater sparing of immediately proximal organs at risk. I think if you were to do a study like that, and it's a good idea, you would want to pick a particular site, right, that has an organ at risk, and not all skin cases do. So a great idea would be, plan 20 nose cases and look at how the orbit is spared. Totally doable. Maybe you're interested in doing that. But
yeah, I mean, some of the prescriptions that we had is about 55-20 gray, where the if it is next to the eyes and lenses, for example, or of so those are the things that I think. I was just wondering whether any studies were done on those.
No, this is quite new, and the study that I showed is the first study that's been done with this tool. But I think compared to electrons, I would hypothesize that you're going to have much better sparing of that nearby eye.
Sorry, I got another question. In terms of if you're treating a scalp, you're creating the bolus onto the body structure. But some of the scalp PTVs that we treat here, sometimes they do goes beyond the where the mask goes away from the body surface. Whether would you have any options of extending the bolus onto the mask, or would you?
Yeah. So this question.
I mean, right?
Yeah, that's a good question. This isn't so much about planning automation, but the mechanics of setup of bolus on the scalp, if I understand correctly. Yeah. So now I switch over to the 3D printing side of Adaptiiv. We have a lot of customers doing extended scalp cases, and the product that they use is called TrueFlex. It is a scalp bolus that is made out of a pored skin-safe silicone. So the way this works is that the mold for that silicone is 3D printed using multi-jet fusion 3D printing, and then the silicone is poured inside of that, and you're actually shipped the silicone inside of the 3D printed mold. So the therapists actually use the mold as a case during treatment. And then you can stretch that bespoke fitted bolus over the scalp. Fits patients really well because it's based on the patient's CT data. And then typically somebody will have a means of immobilization on top of that. For example, a partial mask or a band of thermoplastic that locks into a base plate.
Good. Thank you.
You're welcome.
So we've just got some more in the chat now. So Stefano, do you have any PTV volume constraint for using DermaPlan?
Not on volume, but on depth. We have, the goal here was a suitable and maybe superior replacement for electron beams. So as a rule of thumb, we're sort of putting a limit on the deepest volume that you would otherwise treat with an electron beam. So if you can imagine your highest electron energy in the clinic were 16 MeV, let's say, to get decent fall off with an electron beam, then you're looking at 3 or 4 centimeters depth. But in terms of overall size of PTV, given that depth constraint, we've done some quite big volumes like whole scalp, all the way around, using that second option for VMAT, whole arcs instead of partial arcs.
One from Ridyan. Sometimes it's not possible to physically create the ideal bolus required in the plan. Is there any way of restricting, for example, unrealistic curvature when generating the bolus structure or simulate the impact of the air gaps?
You're getting a step ahead of me here. That would be
I was gonna say
a nice feature. Yeah, like some sort of constraint on the complexity of the bolus, I guess. Well, my own take on this is that if you have a very complex treatment geometry and you want to avoid air gaps, actually, it's not my take, it's proven multiple studies in the literature, you should probably be using some sort of 3D printed bolus as opposed to either attempting to tape superflab, eliminating air gaps, or creating some contraption out of wax or something like that. I've seen incredibly complicated geometries handled well with 3D printed bolus. So surgical defects, surgical cavities, around the fingers and palm for Dupuytren's contracture, it can really handle quite a lot. So our kind of take with this application is we wanted to support simple geometries and allow users to use superflab, simple bolus, where it's warranted, but also to enable the 3D printed style of bolus.
Which is also available through us. So
there you go, Misbah.
Yeah, if you're interested in 3D printing, we can look at that as well. So that's fine. Is the conformal index presented accounting for the entire PTV structure? I'd assume dose spillage towards the bolus would not be an issue for superficial targets from Athena.
That's a very astute comment. So we eliminated the volume of dose in the bolus when we calculated CI, since that would be inconsequential to the patient. And also, we're allowing that dose in the optimization to extend, as it will, into the bolus volume. So yeah, great question. And that applied to all of the metrics that we calculated, that is CI, HI, and GI as well.
Another one from Stefano. Can you combine DermaPlan with nodal irradiation?
Nodal irradiation, for sure. Nodal volumes that would be close to the surface. So I would say yes, head and neck nodes that approach the surface, potentially IMN for breast. Just keep in mind that this really is designed for superficial target volumes, not deeply seated volumes.
One from Richard. Will the system automatically avoid selecting beam geometries which might collide with the couch or patient?
There's no built-in collision geometry here, but all of these arrangements are coplanar, first of all, which will minimize risk. Actually, unlike a lot of electron setups, right, where you're rotating the couch, you would do your normal physics QA after creating a plan like this. So for example, for a very anterior isocenter which drops the couch, you would want to do your normal physics QA on collision avoidance. And most centers would have a measurement off of the couch surface where that becomes of concern.
So thank you, and I hope everyone has a great afternoon.
Thank you, everyone. Bye.
Thank you. Bye.
Bye.